Listen to your talk, Universal Lower Bounds for Discrete Potentials of Spherical Codes of Design.
Okay, well thank you, Oli, thanks for your nice comments. And thanks to the organizers, to the Institute of Mathematics and Informatics at the Bulgarian Academy of Science, Mathematics Department, Mathematics and Informatics Department at the University of Sofia. Appreciate the invitation. It's always good to be back. COVID has kept me away for a number of years, so it's really a pleasure to see every old friends and young friends as well, and make some new ones. Okay, so I'm going to be talking about discrete potentials and spherical codes and designs. You'll hear the word polarization. So this is also, I could have called this sort of polarization of spherical designs. But let me just give you a quick outline. So we'll do some definitions. Let's see if this is working here. Yeah, okay. So it's not showing up. The red dot is not showing up over here.
You have to.
Yeah, it shows up here.
Working outside. Yeah, look. It's working outside, but not on the
not on here.
No.
Not on the screen.
Not on the screen. So how does that? Why does that happen? Okay. Already, I told you I expected technology problems. So this is my first one. But you can see. You can read this. You can read here. So we're going to talk first about some notation. We try. Oh, you mean like?
Yeah.
Like I remember that. When I was young, growing up, we used to have. It's called a pointer.
Yeah.
Okay, so you have a longer one, maybe? We used to have a kind
I don't know.
you can extend, you know.
Yeah.
Very, yeah. But I used to use it to wake up the students who were asleep, you know. Okay, so if
18th century. Open 70th
Thank you. All right. Okay. Anyway, I'll talk about some notation. Then we'll discuss polarization. What is the terminology that I'm going to use? And the main results are obtaining universal, what we call universal lower bounds for this polarization. And then some examples here, including Higman-Sims graph and E8 lattice and Leach lattice. Okay, so everything takes place on the unit sphere, Sn-1, so this is the unit sphere in Rn, so little n is just a dimension of our ambient space. Capital N is the number of points in my code, so just a subset of the sphere. We'll just call that a code, C, and its cardinality would be denoted in the usual way. So a number of results we talk about here are related to covering. The topic of polarization is intimately connected with covering problems. And here's the familiar covering radius for C, the code C. What you do is you look at an arbitrary point, X in the sphere, see what the closest point of C is, look at that distance, and then you maximize over all X on the sphere. That's your covering radius. Expressed in the Euclidean way. So this is the Euclidean norm here. But you can also express it, and it's convenient for us since we'll be working with inner products. You can also look at what is called the inner product form for this covering radius, which is taking it's a min-max problem described here, and that's related in the Euclidean way to just 1 minus the Euclidean covering radius squared over 2, which you just get from this simple relationship about the modulus of the difference of 2 points on these unit spheres squared. Okay, so that's how those are related. And we'll be talking about the best covering radius of a code of cardinality n. So here's the covering radius of a code C here. But if we are given a positive integer n, then we can talk about the covering radius with respect to n. And that's simply the minimum of the covering radii for spherical codes of cardinality n. Okay, so and it's more simply expressed in terms of angular, it's an S of n. So I have to remember to go on to the next slide. All right. So the definition of polarization that we're going to use is unfortunate word, so to speak. We have lots of polarization we don't want to deal with of a political nature. But in this case, what we mean by polarization is the following. You are given this code C. You're given a function h, which is defined on -1, 1. And you form its discrete potential defined here. You just take the sum of h, evaluated the inner products, where y varies over your code C, and x is your variable on the sphere. So that I call a discrete potential. And polarization will have two versions of them. Both of them will be denoted with a capital Q, a calligraphy Q. There'll be a Q with a lowercase h and a Q with an uppercase h. So what is that? Well, by Q with a lowercase h, we simply mean the minimum value of this discrete potential as x varies over the sphere. And if we're given our h, our function h, and a positive integer n, we can then look at such minima and take their maximum over all codes of cardinality n. So that's the so-called max-min polarization. So okay, this is just min polarization. With the superscript here, it's max-min. So I'm going to start talking a bit about the max-min problem, which is a tougher problem, and then go on to talk about just the minimization problem. Okay, so let's a little bit of background if you haven't seen this. By the way, I should mention some popular potential functions h. For us, the Reese S potential, where h is given by 2 minus 2t. T is the inner product of x and y, to a power minus s over 2, or expressed in Euclidean way, it's just the distance between points raised to the power minus s. And I'll just deal with s positive for today's talk. And in special cases, when s, say, is n minus 2, n being the dimension of the space, then that's just the Euclidean or harmonic potential mod x minus y to the n minus n minus 2 power. When s is 0, we usually just denote that but with the law. That's the law. So s is 0 for a Reese potential means you're talking about the log of the reciprocal distance between points. And of course, Gaussian potentials play a very important role in this subject and in many subjects. And in fact, you can express your Reese potentials in terms of Gaussian potentials. Okay, so now let's so let's look at a beautiful picture that I did not create. This is done by Rob Wormersley, and it concerns the Reese potential where s is equal to 1. So this is Coulomb, actually. This is Coulomb. We're on the sphere S2 in 3 space. There's 400 points here, and numerically, Rob Wormersley computed these minimum, max-min. So we're looking at max-min points. So we're looking at the max-min polarization. So you can see these red dots. Those are the red. Those are our 400 points. The green dots are points where the minimum is attained for that particular configuration. So it has beautiful properties, apparently, right? It looks like nicely distributed over the sphere. Of course, we can't find out exactly what these points are, but we certainly suggest that studying their asymptotic behavior might be worth doing. And we've written a number of papers dealing with the asymptotics as the number capital N goes to infinity of the behavior of such points. But that's not the topic of today's conversation. I'll be focusing more on finite sets of points. One of the earliest results on the max-min polarization property is due to myself and colleagues Hardin and Kendall. And by the way, I forgot to mention or emphasize that this whole talk has to do with work that is joint with our colleagues here, Peter Koivulenkov, Maya Stoyanova, Peter Dragnev, who unfortunately couldn't be here, and Doug Hardin. So I'll mention them again as the results come up. Okay, so one of the simplest things is this. You know, you have the unit circle. So I have the unit circle. I want to put endpoints on the circle in such a way as to maximize the minimum of the discrete potential in those endpoints. And max min problem on the circle. And the answer is going to be obvious. Okay, they should be equally spaced, it would seem like, for any reasonable potential h. So here, I'm assuming only that h is a function of Euclidean distance between points where that function is decreasing and strictly convex. So that's a kind of standard assumption for a lot of these problems. And it turns out, indeed, these points are equally spaced. And it was a little bit harder to prove. I thought it was going to be trivial at first, but it didn't seem that way. Later, more recently, Zillard and colleagues have another proof of this result, which is very nice indeed, that I recommend you look at. Okay, so that's points on the circle. So let's go from a circle to a sphere, say the sphere of dimension n-1, embedded in Rn, and what can we say about that? Well, Sergei Baratychev proved the case where capital N is between 2 and n plus 1. So as you might imagine, if you're on this sphere and you have just 2 points, it's the North Pole and the South Pole. If you have 3 points, it's 3 points on the equator, essentially. If you have 4 points, he was able to prove that it's a simplex, okay? That if you're, I'm talking about S2. But in general, okay, it's a simplex if you're in Sn minus 1, that it's optimal. So expressions we've seen the other day, where we have a Minkowski distance, and we raise it to the 1 over s. And as s goes to infinity, this simply has a limit, which is 1 over the covering radius for that constant, for the configuration C. And furthermore, for fixed n, if you're looking at a fixed n situation, you can optimize, look at the optimal point for each n given by s, and take its limit as you raise it to the 1 over s power, and it gives you the covering radius for the optimal covering radius by n points for the sphere. Okay. So how do you prove this? So it's really trivial. So here is our expression. So this is our discrete potential here for our configuration C, capital C. We have this expression raised to the 1 over s power. We can certainly replace this expression below by just looking at the largest term. Just pick out the largest term here. In other words, where this denominator is smallest, and that certainly is going to be a lower bound. An upper bound will be, okay, you got the largest term, which would be 1 over this min, and then how many terms do you have here? You have the cardinality of C, and this is all raised to the 1 over s. So you have this bound both above and below, and as you let s go to infinity, okay, so I want to first take the minimum. Let's take the minimum of across the board here. So the minimum of the central term here is just the same thing as our polarization, and the minimum of this quantity is simply the cardinality of C to the 1 over s divided by, well, the minimum of this is the same as taking the maximum in the denominator, so it's like a 1 over max min, or this gives us the covering radius for the configuration C. So you let s go to infinity now, and you see that you get the desired result this way. Just let s go to infinity, and you see this quantity is forced to go to 1 over rho. See, an analogous argument if we're talking about the max-min problem for a given positive integer. Okay, so it's really a triviality, but actually I need it later. The same kind of argument will turn out to be useful for a result later. Okay, so now let me get to the heart of the matter, which has to do with polarization for spherical design, spherical tau designs. So probably we all know what is a spherical tau design. So first of all, we're talking about a code C on the sphere of dimension n-1. And what a spherical tau design is a collection of points with the property that if you take any polynomial in n variables of degree at most tau and integrate it with respect to just the uniform measure on the sphere, the vague measure, surface area measure on the sphere, normalized. That's the same thing that you get as if you take the average of your function, your polynomial, in those discrete points. Okay? So that is a spherical tau design. And the strength of a code is simply the maximum of such numbers tau, so that C is a spherical tau design. Okay. So Gegenbauer polynomials play an intimate role here, and I just remind you of the definition. Gegenbauer polynomials come from Jacobi polynomials, classical Jacobi polynomials, but they're equal weight Jacobi polynomials. In particular, the parameters are n-3 over 2, n-3 over 2, and we will work with it. These Gegenbauer polynomials are normalized to be 1 at 1. So, and they are orthogonal polynomials. They're orthogonal with respect to this measure mu with a subscript n, so given here, and that's a probability measure as indicated below. Another way to define these Gegenbauer polynomials is recursively, so they satisfy a three-term recursion relationship. But the most important thing for us, in fact, is that is a triviality, that if you take any real polynomial of degree at most k, you can represent it in terms of this basis of Gegenbauer polynomials here. And the coefficients are denoted by f sub I. And the most important coefficient here is f0. Okay? For our purposes, f0 is the one that's going to really make a difference. Okay? And we'll also need what is called the adjacent Gegenbauer polynomials. What is that? Well, that's if we take one of those superscripts and perturb it by 1. Perturb it by a. So a or b, that could be 1. And so that we call an adjacent Gegenbauer polynomial, and that just affects the orthogonality measure in this way. And again, we normalize by making him equal to 1 and 1. So, all right. Okay, so here is a famous result, simple result actually. Those of you working in spherical designs sure know this, that an equivalent way to define spherical tau design is that a code is a spherical tau design. If you take any function f, a polynomial function of a single real variable of degree at most tau, then and form its discrete potential, then that discrete potential is constant on the sphere. So for all x, okay, this sum is equal to the quantity on the right, which is just that 0th coefficient, the Gegenbauer expansion of f, times the cardinality of c. Okay, so everybody knows this, right? No, sort of. All right, let's prove it, okay? Just in case. So let's just, yeah, all right. Let's go ahead and do that. So let's do a proof. I remind you of spherical harmonics. So this harm of k, that represents all the homogeneous harmonic polynomials in n variables of degree k. And this Rkn is a dimension of that. That's a vector space, and that's its dimension. And then we form a basis for this space of polynomials, and that's classically denoted with this Ykj of x. And so these are orthogonal polynomials. Each polynomial is of degree k in these n variables, and they're orthogonal with respect to n-1 dimensional surface area. And these functions, these polynomials that are harmonic with respect to of degree k are orthogonal to those which are harmonic and of degree j naught k as well. So okay, so we have that property. All right, now the key is the addition formula, well-known addition formula for spherical harmonics, which says if you take the sum of this product of these spherical harmonics, first in the variable x, then multiply it by the same polynomial in the variable y, and sum this up over all your basis polynomials, it depends only on the inner product between x and y. It only depends on the angle between x and y. Okay? It's zonal, what we call zonal, right? And in fact, it's equal precisely to the dimension of your harmonics polynomial space times the Gegenbauer polynomial of degree k for dimension n. Okay? So that's where everything sort of flows from, this addition point. All right, so let's look at a consequence of this. So simple consequence of this is the following. Let's start off with a tau design. Okay, so C is a tau design, and k here is between 1 and tau. And let's look for the moment at this discrete potential here, where I look at a Gegenbauer polynomial of degree k, and I sum up over all points y in our code C. So I can write this sum if I replace the polynomial here by the addition formula representation of it. So here's, I've just done that here. Replace pk by the expression in terms of the product of these y's. And then I've kind of put in red, I've interchanged the order of summation. And I put in red here something that looks exciting, because here we have the sum over points in the code of a polynomial here of a degree at most tau, right? So I know by the definition of a tau design that sum is the same as the cardinality of C times the integral of that polynomial over the sphere. Okay, but that integral of that polynomial of the sphere is the same as this integral times 1, right? And that's orthogonal. You have orthogonality, so that's 0. So this sum here is 0. Okay, we have that sum as 0. So what does that mean? That means if you have any polynomial function given here, represented in terms of the Gegenbaur polynomials, and then you look at the sum of its discrete potential, you're just summing up all these terms here, and so you get 0, except when what? Except when k is 0. So for all k between 1 and tau, we get 0 when we do that. So what all that's left is the 0th term, and that's the proof of the result. So because that's so important in what we're talking about, I hope you enjoyed the proof of that. All right. So how are we going to, our goal is to get lower bounds for polarization. We want to say something about the minimum of a discrete potential for a code that's a spherical design. So how do we do that? Well, one way to do it is to use some kind of linear programming method, and that's what we employ. We first look at polynomials denoted as sort of a good class or admissible class of polynomials here. This calligraphic L, and what is that? Those polynomials of what we call admissible polynomials, which are all polynomials of which are of degree at most tau, and stay under our potential h. Okay, so they stay under the function h on the interval -1, 1. So these are our sort of good polynomials. And then it's a triviality here. This next result is a triviality, right? Because what it's saying is that if you've got a positive integer tau and you form the discrete potential in this code C, then certainly it's bigger than or equal to the corresponding potential for an admissible f. So if we take an f from this class, it's lower bounding h, so we have this inequality. But we know that if we have a spherical tau design, that whenever we have this polynomial discrete potential, this is equal to f naught times the modulus times the cardinality of C. That's the result we just proved. Okay. So that's a kind of trivial thing. So if we want to improve our lower estimate on this discrete potential, what do you want to do? You want to maximize this right-hand side over all possible polynomials in this admissible class of polynomials. So admissible class just means it's a degree at most tau, and it stays under our function h. Okay. And so this is just a very restatement in some sense, that if you have a collection of tau designs with cardinality n, and that's a non-empty collection, then its minimum polarization is always bigger than the maximum of that right-hand side. We just make that right-hand side as large as possible. And so how do you do that? How do you make that right-hand side as large as possible? You solve this linear programming problem, which is you're given your dimension, your tau, capital N and cardinality, and your function h. You want to maximize, well, over f naught. So and only deal with functions that are in the admissible class. And so that leads to the following main result here. So the main result that's due to Maya, Peter Dragneff, and my colleague Doug Hardin, and also Peter Poikol-Lenkoff, is that if you have a spherical tau design of cardinality n on the sphere, and you let tau be 2k minus 1, well, we can allow it also to be 2k. So epsilon here is either a 0 or a 1. So this is going to depend on the cardinality, or the parity, so I should say the parity of tau. So for most of our things, we're just taking tau to be 2k. You can just think of tau as 2k minus 1. And we assume that h is our function, our potential function, which is continuous on -1, 1. It's finite on the open interval, and it has a derivative of order tau plus 1 that's a constant sign. So it's either always positive on the interval or always negative on the interval. Then we get this lower bound for the polarization. So the polarization lower bound is given by n times the sum, an expression here that will involve what are called weights, that are these rows of i's, and our function h evaluated at points alpha j here, I think it's called, or alpha I, yeah, here, alpha I, thank you. And that's, what are these alpha i's and what are these rows? So the alpha i's are quadrature nodes for the Gegenbauer that you get from Gegenbauer polynomials. Okay, so the Gaussian, if you think of Gaussian quadrature, you have orthogonality measure, and you have Gaussian quadrature. We use Gaussian quadratures I'll talk about in a minute. And so these nodes are coming from Gaussian quadrature. These are the corresponding weights, and they're positive. They sum up to 1. And these, more precisely, these points, the quadrature points, depending on whether this constant sign is non-negative or not, we take the zeros of either this polynomial, which is just perhaps an adjacent polynomial if epsilon is 1, or just the polynomial itself, where if h, the tau plus first derivative is negative, not positive, then we take the zeros of the polynomial, the Gegenbauer polynomial, where we allow points at 1 and minus 1. So depending on whether this constant sign is positive or negative, that will affect our quadrature points here in this lower bound. All right. So the weights, how are they determined? Well, this is our measure we've seen before for our Gegenbauer orthogonality. And the weights given here, expressed here, are typical way to represent weights, where in terms of integrals of the Lagrange basic polynomial. So what's a Lagrange basic polynomial? It's a polynomial that's equal to 1 in alpha j and equal to 0 in all the others. Okay, so that's the guy there. So and so okay, so that's the result, and it's best possible result that could be obtained via linear programming. So that's the lower bound that we're getting, and okay, so what's so great about this theorem? Well, one thing is it's kind of universal, because hey, these quadrature points don't depend on h, right? They're working for a large class h point, so it's universal in that sense. It's also a lot weaker than the typical results that you see for energy type estimates, since for energy type estimates we usually assume that you have a absolutely monotone h. Okay? And here we don't. We've relaxed that substantially. We only have this tau plus first derivative, which is a constant sign that's required here for this one. And okay, and so all right. So one thing we get for free is this corollary. So, and you all can prove this corollary. So what does it say? It's due to Fazekas and Levenstein. And it says if you have a spherical tau design, okay, the cardinality is indicated as n here, and tau is 2k minus 1 plus epsilon, then the angular covering radius, which is equal to this expression in terms of the Euclidean covering radius, is bounded below by the largest zero of this Gegenbauer polynomial. And that's the classical inequality there. So you can prove this. How are you going to prove this? I'll take a drink of water while I'm up here. It's like my class back home. Decided to be very quiet, too early in the morning. So how do you prove it? I mean, this is so we just gave a proof, right? All you need to do is take your h in our theorem, replace it by our Reese potential, h sub s. Let s go to infinity. And we show that if you do that, the left-hand side, you'll get out this expression, you'll get the expression involving rho of C, and on the right-hand side, you use the quadrature, okay? The expression in terms of the quadrature. So it's the same argument as the one we gave earlier to get this lower bound on it. So this is a lower bound on the angular cosine, so it's an upper bound on the Euclidean covering radius for these codes. Okay. All right, so what about the proof here? Well, as I mentioned before, these alphas that come in the right-hand side are just Gauss-Jacobi quadrature points for our Gegenbauer polynomials, and so that's where the alphas are coming from, this quadrature. And the other part to this puzzle is using Hermite interpolation. So you want to construct a function h. You want to do for our given h, you want to construct a function f, which stays below that function h, right? So what you do is you interpolate h in these nodes, the alpha i's from the quadrature, and you interpolate them doubly. You interpolate the function as well as its derivative, and that kind of allows it to stay underneath for the whole interval. So that's the crucial condition why we need that tau plus 1. Remember the tau plus 1 derivative? Well, tau is 2k minus 1. Tau plus 1 is just the 2kth derivative of the function. So you can see that's where we're using, say, the non-negativity, the constant non-negativity, so that this difference is greater than or equal to 0. So this interpolant stays below h. So that's sort of the crux of the argument. All right. So there's also the issue about when equality holds, and does equality hold for some of our favorite designs? That's the other issue. Yeah, when does equality hold? Well, if and only if in our lower bound, if and only if you can find this point x tilde such that if you look at the collection of inner products of x tilde with the points of our code, then it coincides precisely with our node set for quadrature, the alpha ox. And moreover, that if you take the cardinality of your code and multiply them by the weights, then these should be integers. These are the, in fact, give you the multiplicity of those inner products, okay, as they appear. Okay. So some examples of this. So let's talk about some examples. What about the cube inscribed in S2? Okay, so I have a cube C naught. I think we'll all agree it has 8 points, and you can show that it's a 3 design. So the 3 design tells me what? 3, my k is equal to 2. So that tells me I have to look at this p sub 2, the quadratic, in 3-dimensional space, since I'm talking about a code on S2. All right. So that's simple enough. That gives me alpha 1 and alpha 2 plus and minus 1 over the square root of 3. The weights are equal at 1/2, 1/2. And so the bound that we get from the main theorem states this, that for any such code C that satisfies conditions that the cardinality is 8, and it is a code of a spherical design of order 3, that it's bounded below by this quantity here. And the cube attains that lower bound, because if you take the north pole as your x tilde, then and use that result that characterizes equality, you get precisely the node points and to the right multiplicity. Okay, so it is the universal optimal code with respect to polarization. The word didn't come out on here. Okay. Other examples. So on S3, a popular, you know about this, right, Oli?
Yes.
Oleg knows about this one.
I will show you some pictures.
Okay, Oleg's going to show us some
Remember.
pictures here. All right. So we're talking about on S3, and I'm talking about a collection of 24 points and a design of order 5. Okay, so it's a 5 design. So our K here is 3. So we have to look at the cubic in 4 dimensions, and these are the zeros here. The quadrature nodes are indicated as shown. Our lower bound that we get is precisely what's in this display 7. And Oleg's favorite design, right, the kissing design. Okay, and that in fact equality holds for that kissing design. And
Wow.
is that good?
Very interesting, extremely interesting. This is
Okay.
I never know that.
Okay, and so if you take, okay, so you know, typically in this case, there's a couple of choices for this x tilde. So the x tilde is sort of the point that's furthest away from your configuration. Okay, that's what you're really looking for. So sometimes it's kind of obvious. It's sort of, you look at the spherical caps that are formed by the configuration. Sometimes you can kind of guess, but there are a number of times when you can't guess very well at all. Okay, it's not obvious. And so one other class that we all know and love are the sharp codes, right? So the sharp was a sharp code. A sharp code has the property that it has k distinct inner products, k between distinct points of the set, and it's a spherical 2k minus 1 design. So this is a Cohen-Kumar stuff, that to be a sharp code. And when we deal with energy, so this is the definition of the H energy, where we just sum up the interactions between xi and xj for any endpoint configuration. That Cohen and Kumar 2007 proved that the famous theorem that if you take a sharp code, then it's universally optimal with respect to energy. Okay, and that is if you take any H minimizing configuration where H is absolutely monotone. Okay, then using that code will give you the minimal possible energy for the whole class. So what we did was we looked at all these examples of sharp codes that are known and said, well, can we come up with a sharp codes in the sense what a sharp code where we have equality for polarization? Do we have equality for polarization? And so here's the table. It's almost the complete table that they had. So that's where we lifted from their paper. I think we left off the bottom one, right, which was this kind of general class, which we're still working on. But these are essentially all the popular sharp configurations there are. Okay? And in fact, we get sharpness, and here's our formulas for the lower bounds. So this is the universal lower bounds that are actually attained for these sharp codes. And so we get these except in 3 cases. Okay? And those are the ones in red. There's one case here which is in boldface, and that is a case of 100 points, which is a kind of was a challenging problem, and even more challenging to explain in detail. So I'm just going to go over it very quickly, and that has to do with a strongly regular graph. So in particular, what is called the Higman-Sims graph. Okay, so this is a strongly regular graph which consists of 100 points. So we're talking about 100 points, this is the general notation for a strongly regular graph. You get 100 points. It's got degree k. In this case, it's 22. So there are 22 edges going into every one of the points. So every one of these points. So these 100 points are on this outer circumference, and they're connected to 22 other points on here. Okay, and it has the property that that two adjacent points, 2 points that are connected, don't have a third point. So there's no triangles in this. In this picture, there's no triangles, right? But if they're non-adjacent, they have exactly 6 points in common. Six. So it's a pretty cool graph, right? And so you can convert this to points on the sphere, as you probably all know, right? You look at the adjacency matrix that you form from the strongly regular graph, and you look at the eigenvectors corresponding. In this case, I think there's 3 different eigenvalues. You should look at Brouwer's book on strongly regular graphs for this. Anyway,
What's the dimension of the sphere? Is it the slope or is
no, it's S21, S21.
Yeah.
So what we're talking about here is S21, 100 points, and it turns out that it is a design order 3, a 3 design. Okay, it's pretty cool stuff, right? So if it's a 3 design, we have to look at the quadratic, okay, the quadratic polynomial that corresponds in dimension 22. All right, and here are the roots, simple enough, right? And they each have weight 1/2, of course. And so the claim is that the minimum of this code, talking about the minimum polarization, is given precisely by this expression. For any h, any h is 4th derivative is non-negative. Okay, and that this is this minimum. We know from our theorem that it's greater than or equal to this guy. The challenge was to prove equality, that equality holds, okay? And so in other words, we need to find this magic point x tilde. There'll be hundreds of them, I think, right? For which you will have, because the weights are 1/2, so which you have 50 points where the inner product is -1 over the square root of 22, and we're 50 points where it's +1 over the square root. So the challenge was to find this x tilde, and so that turned out to be substantial. What we do know, and what was helpful in this process, was knowing for the energy bound, knowing the inner products. We know that there are 77 points for which the inner product. You just pick 1 point from this collection of 100 points. There are exactly 77 points where you get a inner product of 1 over 11, and there are 22 points where you get an inner product which is -4 over 11. Okay. How much more time? 5 more minutes and a half?
Yeah. We've got
Great.
4 minutes.
Okay. This may work out. I might finish actually. Okay. So this is for this. This is a sharp code. Okay. So there's a sharp code, and this is the Kumar result right here. Okay. But that's not what we're after. We're after the polarization result here. So we have to find this x tilde, and so this involves a substantial effort, because what we have to do is figure out another way to put these points on the sphere, such a way that we can take out x tilde. So one way is to use this adjacency matrix and all of that. Okay. But does not make it obvious. But if you work with a binary Golay code, G24, and there's a lot of the things that have to be done here, like lopping off the starting digit and so on and so forth, you're led to what's called the M22 graph, and after a lot of effort, we're able to produce the x tilde. So I won't go through these details, but it takes a lot of dancing around, so to speak, to go through different graphs. There's another type of graph, this Hoffman-Singleton graph, that comes into play, that is used, and so on. So there's a fair amount of graph theory involved in finding those points, but we're able to find those points to prove the equality holds. So what about the exceptions? So remember those red guys that were in the sharp code list. Those are the exceptions. And what do they include? They include the icosahedron, one of our favorites, the E8 lattice, and the Leech lattice. Okay, what do we mean by the E8 lattice? And we mean the vector is the shortest length, okay, on the E8 lattice, and likewise for the Leach lattice. So how to determine they do not attain the lower bound that's in our theorem. So, okay, so what do we do there? Say, oh, what do they attain? What is it? What can we say? And so what we have to do to deal with this is move on, go beyond tau designs to what are called T designs. So this was an invention of Del Sart as well. Del Sart and Del Sart, T design. So what is a T design? So T is just a set of integers, and a code C is said to be a T design if, hey, you got this magic property of equality, constant on the sphere, right? Holds for the case of polynomials, Gegen-Bauer polynomials, whose subscript belongs to this set capital T. So capital T is a set of positive integers, and what we require is that this is equal to this equality holds here. Or you can also define it in terms of moments, vanishing moments. So the moments are going to, for the code are going to be, okay. So I mean, so what is it? What is a tau design? A tau design is a capital T design where your capital T is all the integers from 1 to tau, right? The point here is that we're leaving out some of these integers, okay? And that's how we get it. So what is our trick here? It's something that we used in our previous work on energy results, and it's called skip 1, add 2. It sounds like a dance or something, right? Skip 1 and add 2. So what are we doing? Here's our set that we're going to use here, set T for our T design, and we're going to go from 1 to 2k plus 2, but we're going to remove the 2k. In other words, we're going to look at only the span of Gegen-Bauer polynomials up to degree 2k minus 1, together with the two 2k plus 1 and 2k plus 2. So we skipped over that 2k degree 1, and we're going to work with this subspace. So the idea to get the results for those 3 exceptional cases is to use this technique. Oops, are we losing connection here?
Yep.
Recording in progress.
Okay.
Yep.
Sorry. Still in progress? Are we still in progress? Okay, great. Okay, so here, what is the challenge? So we're dealing with a subspace now of our Gegen-Bauer polynomials, and so what we need is to find our, so to speak, quadrature points. Okay, how are we going to do that? So what we do prove is this lemma here, which says that if you take a linear combination of pk plus 1 and pk minus 1, then you get a polynomial with the property that its zeros induce a quadrature rule with respective weights gamma I, and is exact on this subspace polynomials. Okay? So working on that subspace, we want to prove there exists a quadrature rule. Okay. All right, so now it's not advancing.
Zoom thing is still.
So something you must be. Oh, this is Zoom.
Yeah. Just give me a second.
Okay.
First high video.
Almost done here.
Well, it's gonna stay on like that. Just hope it doesn't.
We need to advance to the next slide.
Само да не знам дали сега ще го работи.
Okay, so this is the generalization. So we now have a generalization of our lower bound for polarization that applies to T designs. And this is precisely it, and it's based on the zeros of the polynomial we produced in the lemma. And when we do that, we get our next slide, which is this. We get a precise lower bound in those 3 exceptional cases that I mentioned. So this is the icosahedron, this is for the E8 lattice, and this is for the Leach. So Not something you would guess for a lower bound, but it's sharp. Okay, this is a sharp lower bound all we need in this case is just the tau plus first derivative is non-negative on -1. So I think I'll stop here. Thank you.
Thank you for the presentation. Question?
What's the reason for the exceptions? Why do they come up?
I don't.
What's the reason for the exceptions?
Why do they not fit the general framework? What is the physical underlying reason? Is there any?
Not that I can think of off the top of my head specifically.
Or an analytical reason?
Yeah,
or something?
yeah, I don't know. I don't have a good explanation. It's just seemed to come out. We had a similar situation for, well, what's similar? It's sort of like the 600 cell, right? We deal with energy, and there was a case of the 600 cell.
Yes, but 600 cell was exception in the energy problems also. These were in line with the energy, but here they are exceptions.
In the other case,
Yeah, it's. I don't have the, I don't.
Yeah,
Thank you for your interesting talk. My question is there is a difference between functions on cubes and on spheres in your framework?
No.
No?
Difference, you mean work with codes on this?
Sorry, I don't for the previous question. I'm sorry.
Is there is a difference between functions on sphere and on cube in your framework?
Points on sphere.
Well, we can't, right now, what do we use in terms of spherical harmonics?
This is
No, it is not.
No,
It's not geometric cube.
Yeah,
It is
yeah,
like
this is the
points
cube
on
on the
sphere.
sphere.
We're talking about points on the sphere.
Yeah,
from topology.
yeah.
Cube
Not topology. Topology, okay. Just configuration. They call it cube only because it is form of cube.
Yeah, so we work on sphere, but we can also work on
So
general.
say curvature is not influence.
So we have some generalizations beyond the sphere to other spaces, right? That we're doing plan for the future.
Okay.
So you had some exceptional cases, and for that you had a different result, a different bound that they were satisfying. Were any of the, say, non-exceptional, tighter, sharp designs, did those also satisfy the second bound?
No.
I think so.
Because most of them are not TK.
Yeah.
Okay.
I have many questions, but
Okay.
They are better, and this is why they don't satisfy the thing. They're quite better to give it to on the first.
Yeah.
okay, a number for a small number of points, right? Do you have some list of points? Say, okay, we have 5 solids, right? Photonic solids. Cube is, right? What about octahedron?
It's okay.
Yeah, the
Okay,
octahedron
okay.
is always okay.
Cube, icosahedron is not.
Yeah, icosahedron.
What about the tetrahedron?
Yeah.
It is, the tetrahedron is dual, right?
Tightly designed.
It is
It's okay.
Yeah, you know, why I ask you, because, you know, there are two, you're familiar with Fullerens, right? And actually, people looking for some optimization, why Fullerene is so popular in physics? I mean, we have it in real life, Fullerens, right?
Oh, Fullerene.
Maybe Fullerens is, in your also is optimal. You can can check.
Full arrays are.
No, because consumption is a tool, right? You're right.
Yeah, it's kind of a dual.
And dual
I
issue.
agree. Okay, but it's not it's not a precise dual. Right?
No, okay. Suspicious case is cube, because cube is never is optimal. Never is optimal for
To decahedron also fits.
What?
To decahedron also fits in TK.
It's a great thing, because it's both full array.
Yes, that's a
Cube is full array, dodecahedron is full array, and the dodecahedron is never is optimal for encoding series. Right?
Okay, so
Check it.
here's something.
At least you know you at least maybe this polarization theory because of this. I mean, like the full array causes theory. Maybe it is. Dodecahedron,
Yes, yes. It is like icosahedron, the bound is 5, 5, 5. Icosahedron is 3, 3, 3, 3 all times, and the dodecahedron is 5, 5, 5, 5.
No, ask
5
people, you
times.
know, the dodecahedron is a very bad configuration from our point. The cube also
Very, very good.
from Thomas property.
Yeah, but you can turn.
It is a worst. Cube is a worst from the Thomas.
Actually, Fazekas here and
Yeah, yeah.
Bound say that
Yeah, but you can
That's
also.
would not be too bad.
Yeah, and just a word of advertisement, so tomorrow, a young man here is gonna give a talk, Ryan Mosky on polarization. So I hope I've whetted your appetite for his lecture.
Okay, let us talk
That
about,
main purpose.
let us stop discussion and continue.
Yeah.
Because we have, it's 82 minutes
Oh,
next.
that's right.
Yeah.
That's what you've done. Thank you. Terrible. Figure out why this does not show up.
Recording stopped.
Look.
Our second speaker today is Grigory Kanakiansky. All of us know him, I don't know, many years, right? Already his name already appeared in some presentations.
Yeah, and I would like to say that I'm still alive.
Yeah, this is true because he's also young. Yeah, he's still young. He's still active. Okay, please.
Thank you.
Please start.
Thank you to Peter, to all organizers. You know, in our turbulent, it's a small word for what we have now, turbulent time, it's supposed to meet colleagues and friends and talk about mathematics. You see, be prepared for a short talk because my main idea is to present, I think, at least as far as I know, a new program. And so, let me start. In fact, the title is here, and it's about the problem. Oh yeah, that's here.
No, I think
Yeah. Just looks here. Consider the following problem. I will call a subset of a Boolean cube. We will move it to the Euclidean space a bit later, but let me first start from a Boolean cube, so 0 at once vertices. I will call a subset of it a T-independent code if I'll take any two T subsets, disjoint subsets, then there are convex calls. The convex calls as in Euclidean space, not intersect. First of all, of course, the first question is how much these sets could be. The answer is positive. They can be exponentially large. Therefore, we can enjoy the usual talks about the rate of the code, etc. And we will see. I'll give an easy construction of such sets, and it goes from coding theory. In fact, it's clear what we want to have. I have one convex rule. Then imagine I have another set B. How may happen they intersect? If they intersect, there's a joint point which could be written as some lambda A or some lambda B. It means that these two sets together, two sets of vectors, are linearly dependent. So the question is how to construct the big sets of binary vectors in such a property that they need 2 times t of them are linearly dependent. It was a known problem in a funny statement, but I will talk about it later. Let me go to the next. So one suggestion is the following. Consider some code, binary error correcting codes, which can correct T errors. Let DH be its any parity check matrix. Then we know that property that code can correct T errors is the same as to say that any 2 times T columns of this matrix are linearly independent. Of course, linearly independent over a field of 2 elements. But if they are independent over the field of 2 elements, then moreover, they are independent over Q. Because linear independency, it's an inner property. It's just about determinant. It should be 0 dependency. So if determinant is 0 by modulo 2, if determinant is 0 in Q, in rational numbers, of course it's equals 0 by modulo 2. So therefore, if we have it, we have this. Then, if we take a well-known family of BCH Ogopa codes, we will have that the size will be the size of such a code M will be n will be 2 to the power n divided on t. Or exponential 1, therefore, will go to the rate notation as logarithm of the size of the code divided on n. And then it will says that the rate is at least 1 divided on t.
Can you what the motivation of this one? Log of this function?
If you have a big set, I mean, which grows exponentially.
Okay,
then,
you take exponents. Okay.
Yeah, this is just a note.
How I divided by n?
Because otherwise, because in this case you get a constant.
I see.
Because this rate grows linearly with n, so it's natural to divide on n. On the other hand, it's obvious that the rate cannot be more than this value, log t divided on t. And it follows from very easy arguments. Consider instead of the whole, the property that convex hulls do not intersect. Consider the property that mass centers do not coincide for different subsets. But mass center, we consider only the subsets which has cardinality exactly t. Then what we have, the mass center, the CA, is a vector which coordinates belongs to this set. So t plus 1 possible coordinates. So the number of possible such vectors is just t plus 1 to the power n. On the other hand, the number of t subsets is this, and that all should be different. So that's, if you take the log of it, we will get this.
Sorry, can you make sure that it's joint? So suppose you have two sets which have same center of mass,
Yeah.
but they're not disjoint.
No, I say in opposite way. I say that if they are disjoint, then center of mass is also different. Yeah. That's exactly what I use. So of course from
possibility bound.
Yeah, it's as Sasha correctly said, it's impossibility. Okay, so on the other hand, an interesting random quantity technique. Interesting because I don't know how to make it, if to deal just with binary case, these two persons, they prove that the size of the code grows exponentially with this correct value. So we know that the rate is, we don't know the constant here, but at least we know the order. Here I may stop because I have plenty of time. They work not on this problem, they work on more general problem, which at first glance looks not very possible to solve. A usual problem of finding counterfeit coins. But you have not a balance, but you have a digital scale, which gives you exact weight of coins which you put on the scale. And imagine that even what is most unusual, that you know only two things, that all correct or genuine coins have the same weight, but different coins, the counterfeit coins, they may have different and unknown weights. How to find them? It appears to be this is a number of weightings, this one. And to find the weight of genuine coin is clear, because as you know that number of counterfeit coins not more than t. You put on, you take any 2 times t plus 1 coins and measure their weights. As correct weights appears to be majority times. So after that you subtract it, and after that you may think, the genuine coin has a weight 0, and others, they have some unknown to us weights. Then it's easy to check that it goes exactly that we want to find a matrix in which any two times t columns are independent over the rational numbers, so real numbers, so that's why, because it's 0, 1 matrix. And then this is the right order, but of course we don't know the constant. Okay, that's all about until we have mistakes, errors, and still I do not say how it works with geometry, with Euclidean space. It's both leads to the same definition. You see a very simple observation. Consider any of these non-intersecting T subsets in a code where these convex hulls are non-intersecting. Then, of course, the distance between them hence is positive. The number of T subsets is finite. Therefore, take the minimal of run over all T subsets, and we will say, so every such T independent set has a nice property. They are not only disjoint convex hull, but if you take a small epsilon around them, they still will be disjoint. And of course, the question after that is how much d we can do, how to put them in such a way that the convex hulls will be not only disjoint but separated one from another. Separated, for instance, in Euclidean space, in Euclidean norm, but other norms is also good to hear. Okay, consider for simplicity the initial case, the case when t is 1. So we take only vectors, and then the question which I am asking is a question about spherical codes. Of course, to make them spherical codes, let's replace 0 and 1s and plus minus 1s, for instance, by this affine map. Then we move from, the distance will increase 2 times, but it's more pleasant to have now the spherical code with a special coordinates, only plus minus ones. The length is square root of L. And what we know this, the critical angle or the critical distance. The critical angle is, of course, p divided on 2, and we know or the length is square root of 2 times the length of our vectors. That if we want to have that they separated on not less than 90 degrees, then the rate of the code goes to 0. If we take slightly smaller, then the rate is, the number of points is exponential minor, so the rate is separated from the 0. So therefore, just to think what we want to know, of course, about this new problem, if there is any such behavior, if there is any such critical distance, let me go to the list of open questions. First of all, I don't know, I do hope that it's true that that for any fixed t and n goes to infinity, we may enjoy construction of such codes, well, not construction, distance, of such codes that the corresponding convex holes are always separated on the distance proportional to the length of our vectors. If we put them, now they are lying on the, not unit, but sphere of the length square root of n, so that be proportional square root of n. I know the proof, and it's not well, it's just random, only for segments. Even for segments, you think it's a problem. What you want to have such a problem that if you take 2 points from your code and another 2 points from your code, that you know already that these segments not intersect. Now you want that the distance between the segments which should be enough large, proportional to the length of this vector.
Just a second. You still think that you are looking for codes just in +1 and -1?
Yes.
Or just any
It doesn't matter, because if you go from 0 in bounds to plus minus ones, what happens is the distance is only increasing 2 times. Therefore, why I prefer to talk.
No, maybe you can consider any other configuration, escape configuration and point position.
It's a next generalization which I don't even want to discuss, because when we have points on the sphere, of course the next question is why we restrict ourselves.
But why you need
could you stop for a minute?
Okay, sorry.
Now we have this our 0 mass vectors as plus minus ones. So they lie on the sphere. And of course, everything what I'm asking here, we can forget about this is binary or plus minus ones. So just say, okay, it's spherical code with something new property that if you take any t vectors of the spherical codes in other t vectors, consider their convex holes. They are far apart one from another. So the next question, of course, which is what is the corresponding critical distance, critical angle, as we see in quotient theory, what is the blocking bound for this? I have no idea about this. And the third, let me explain the third question, because it seems that we ask the most what we can. We ask that these convex holes are not only different, they are even far apart. But imagine that what it means from say, I have a point in the space. I know that I know that it belongs, it was, say, generated by T subset of my spherical code. Then I want to know who generated it, these vectors. In this case, I know only that any T which can generate this vector, they intersect. But not much, because what could be such a set of suspicious subsets? Think about the simplex in T plus 1 points, and then any T subsets, they have this property. They have non-empty intersection, but still we don't have one point to say this is, it belongs to every subset which can generate it. So this is the third point, the third question. And it's in fact something what I promised to Sasha, that we will return to a problem which we solved for digital fingerprinting problem for 20 years ago from now. Yeah, but now it's in a different. So that's what I say, it should be star property. Again, about this, even here I have, say, a great hope that such a great distance can be formed. Here I have no even understanding if how it behaves. If it will grow linearly, or we cannot get it. And something about the similar problem, but we will see that it's a big difference. There is such a notion, superimposed codes in Euclidean space. It started from this paper of Ericsson and Bjorfi. Then Furudin and Rozhinka improved the upper bound, which was here. By the way, what they did there, they just used the Brickfield type bound for these sets. And Daniel Danev, as I'm Bulgarian, I should mention it. He worked on constructions. I don't want to talk here about constructions. I just first ask about existence of the codes. So explaining what they are doing on the language of my talk is the following. We again forget for a while about the convex holes and thinks about only mass centers. It's not exactly their case. The mass center, I should take the sum of the vectors and then divide a number of the vectors. And they were taking all the sums. And they wanted to have the sums of the vectors should be different one from another. And of course, it's much easier looking problem, but still something known. That's the end. Thank you for your attention.
Thank you for your interesting presentation of the problem. Any question? Comments?
If you forget about special kind of coordinates, plus minus 1 of square root of n, to get any real coordinate in the center, it should be hopeless.
No, why? It means that it depends. No, it means code the speaker.
Sorry.
So then you have more freedom. Therefore, if you have, I will continue to say binary such set, then of course you may enjoy just to have more points. The question is the same as for ordinary codes. I mean, ordinary spherical codes. When your angle is 90 degrees or more, you cannot gain to have arbitrary coordinates, not only plus minus ones. When you go for the case when you have non-zero rate, then of course you can have more. In particular, because the cube is only 2 to the power n. And on the sphere you can find as many points as you want. And you can still enjoy the distances linearly grows with the dimension. So, but why I was talking about only plus minus ones? No, probably because first was I show how to construct them. It's one question. Secondly, I do not think that there will be that the answer on these my questions could be different for modular case or just plus minus ones.
Maybe just to give. Can you explain? Suppose we have instead of a cube, we have a cross polyton. Can you give answer for all these equations?
Cross polytopes, how many points do you have?
2n.
So that's it. I'm talking about exponential endpoints.
No, okay, but you can ask this question.
No, because I'm interested in exponential endpoints.
Okay.
You can ask this question. Probably.
You can ask this question. For instance, the second one.
What is the second?
Critical point distance.
No, I don't think it's in fact cross polytopes.
Okay, so do we have a critical?
But that will not make sense to what he's asking about the critical point, the rank, that where we have the exponential.
Yeah, so we have only we have only cube, right?
No, you can take any again.
Any family there's rows exponentially, right?
Any points on the sphere. But when I against cross polytopes, because number of points is small from the very beginning.
Yeah, but
in the cube they have a nice structure, good symmetry group, and third I have exponential many points. So I do hope that I find exponential many points inside with prescribed properties.
But we have no any natural family. I mean, like discrete family, only cube. We have.
No, I started from the BCH course. I wanted to check if I can check there from the point of. Okay, I know that they are not intersected, hence the distance is positive. But I failed to find the distance.
I know example. What about this? How it's called? This weighted code? What? Weighted code. I mean, like it's also exponential. When the number of this fixed number of ones, how it's called? This? Constant rate. That's right. It is gross exponential.
Yes, of course, and it's a subset of the cube. So by itself, I don't think it's a good code, but you can take.
But it is special, yeah. It's not like exactly cube.
Yes, of course, you can restrict your problem just saying that you want to have this set located there. Yeah. Then to have exponential many, you should have that weight grows linearly with dimension. The best way is to take weight is half of n. Then, roughly speaking, you got again a cube by the number of points.
More questions?
So in this problem one, so L is square root of dimension, right?
Yes, it's just the length of, it's just to think if you replace cube on any spherical code, L is the radius of the sphere on which the point is.
Then you conjecture the answer is yes, right?
Yes.
More questions? Okay. Thank you.
Good afternoon, welcome everybody. I'm still at Davis and the sphere chairman because Oleg Pikur transferred to me this duty. So I'm dropping into coding theory. The first lecture today will be delivered by Alexander Bard, and he will talk about binary codes with 2, 3, and 4 distances. So please.
Thank you. Thank you. So there will be no spherical code. Well, there will be tangential mention of spherical codes today, but mostly it's in the binary world. And let's look at the problem. We have a metric space, and after a few clicks it will become the Hamming space or its relatives. Having a finite set inside M, such as X here, let us look at distinct distances between pairs of points in X, distinct points. So d of X is the distance set of our code X. How many different distances do we have? And we are interested in the following quantity. If the cardinality of the distance set is S, what the largest code we can have for that S in our metric space? A classic problem, both in spherical codes and in combinatorics. Looking back at classics such as Belsard-Kotel-Seidel, we already find two distance sets and few distance sets, and of course equiangular lines that we heard about yesterday from Yufei. They are also a particular case of this few distance problem. So the earliest paper that we know, we are aware of, is by Einhorn and Schoenberg, and they looked at few distance sets in the Euclidean space in Rn, Belsard-Kotel-Seidel, and then, well, I'm skipping many things within combinatorics around works of Roychoud-Wilson, Erdos-Corrado, Frankel-Furedi, and so forth. But then Oleg somewhat revived this subject in the framework that closer to my interests in 2009, when he brought up this problem. Hiroshi Nozaki is also not here. Also made a few important steps, and there are many papers. Have been many papers after that. So spherical two distance sets, of course, are linked, as we all well know, to strongly regular graphs, starting with Belsard-Kotel-Seidel, and the signal processing community picked them up at some point, rechristening them tight frames. More elaborate is finite unit norm tight frames, but then it contracts to fantifs, so they like fantifs very much. And indeed, there is a fantif if and only if there is a strongly regular graph. There was a paper that made clear spherical embeddings of strongly regular graphs due to Belsard-Kotel-Seidel, but Banai explained all the details. Sean Waldron from the signal processing side worked on equiangular tight frames and SRGs, and he has a whole book on that, published recently. So for me, our metric space is the binary Hamming space, or the set of all binary vectors with W1s and minus W0s in combinatorics called the Johnson space, binary Johnson space. And I'm interested in few distance sets in these two spaces. Right, so what was known until recently? For small n, with a few exceptions which I'm not mentioning here, it was known that if we look at codes with two distances, two distinct distances, so the maximum size is n choose 2 plus 1. How do you construct such a code? Well, it's very easy. You take all vectors with two 1s and n minus 2 zeros, there are n choose 2 of them. The distance between distinct vectors of that kind is 2, and then 2 or 4, I'm sorry, 2 or 4. And then we can add the all zero vector without disturbing that picture, and that is the plus 1 thing. So we can't construct such a code, but proving that there can be no codes of larger size was a problem. And well, for small lengths it had been shown, but this was the extent of what was known. Then Oleg and Hiroshi Nozaki did a similar obtained a similar result for 3 distances, and that was based on a beautiful extension of a result from Larman, Rogers, and Seidel about codes with few distances that Hiroshi came up with shortly before this work. Other known results: if the distances are known, A and B, and A plus B is less than n, right? Then this is the maximum. That was our work with Oleg, but this comes with a qualifier, A plus B less than n, so that's not really general, fully general. There was a recent work by Peter Boivalentov and Konstantin Delchev and the Zinoviev pair. They showed that if the distances are specifically 2 and 4, but the alphabets can be 2, 3, or 4, then the maximum size is again that. And for the Johnson space, now with no attributions, because there would be many, some of these papers, 2 distances and the weight is 6, then the maximum size is n minus 2, choose 4 for those lengths. And slightly more generally, if the weight is 3, 4, 5, 6 and the lengths are, the n is r as shown, then the maximum size is n minus 2, and w plus 2, choose 2, of which this is a particular case which appears here, but I isolated that to illustrate this type of results somewhat better. There were results for 3 distances, and well, that's where it stood. And since Gregory and Oleg and Hiroshi just walked in, let me again point out that I'm relying on their works. This is Oleg, this is Hiroshi, and so forth. Right. So let's see what do we get. We prove that in the Hamming space, the largest codes with 2 distances are of that size for all lengths. 6 and more, well, maybe it's okay not to have 5 and 4. And then for the Johnson space, we can do the following. If the weight is 4, 5, 6, 7, and the number of distances is 2 or 3 or 4, then the size of the code is that, starting with n, as shown in the bottom row. So it sort of solves this problem for small weights, 4, 5, 6, 7. And there is one particular case where the weight is any, but then the number of distances is w minus 1. So everything but one missing distance. And there we also know the answer. Well, that's what we can do. And I'll explain how one can prove those results. So for the Hamming, in fact, it was easy for us because it was previously difficult for someone else, and then we relied on that difficult work to obtain our result. Namely, the first theorem goes as follows. If n is greater than 6 and the distances are a and b, then the maximum size is 1 plus n choose 2 unless a and b, the distances, are of the shown form for some integer m, and the dimension relates to m as shown here. So it's a bit complicated to absorb, but this comes from a work on spherical 2-distance sets. So what we do, we take our binary code, we put it on the sphere, as has been done today already more than once. And then we look at Glaser and Yu, 2018, where they established the maximum size of spherical 2-distance codes. And this gives the answer, except for apart from the exceptional cases, which require an additional effort. A lemma is lifted again from that paper, and well, we deal with exceptional codes. That is somewhat computational, so I'm not explaining this in detail. And we show that the exceptions cannot give rise to large codes, and then ultimately this establishes the result. So that's it for 2-distance sets in the Hamming space. Let's move to the Johnson space. Well, for the Johnson space, we write on Delsart. Again, we saw linear programming already in Ed's talk earlier today, and of course this is very familiar. So let's see, be a constant weight code. So constant weight means that every vector in the code has W1s and S distinct distances. So suppose that the distances are D1 to ds. And by the way, in the Johnson space, we measure the distance not as the Hamming distance, but as a half of that. The reason being that if there are two binary vectors with the same number ones, then the Hamming distance between them is always even. So we can divide it, we can take a half of that to make this simpler. And that's what people do and call this the Johnson distance. So Delsart says that the size of the code is bounded above by this linear form where the coefficients are non-negative, and Delsart's inequalities take the discrete Hahn polynomials psi k, substitute the distances. Well, this is the polynomial of degree 0, which we put to the right, but in principle it just says that the linear combination of the Hahn polynomials with these coefficients f is non-negative, right? This is non-negative definiteness of spherical functions, if you like. So this is the very basic result that applies to many, to all two-point homogeneous spaces and so forth. Now, this theorem, of course, is powerful, but it's also difficult to work with. So what is the idea here? Well, in fact, if you look at the calculations, it turns out that not all of these inequalities matter. In fact, only a few. If you satisfy a couple of inequalities, then the rest will be satisfied automatically. And maybe that's already enough to establish the result. That is what we shall do. Let us prove the following result. Let's say there is a code in the Johnson space with two distances, d1, d2. So let us take the degrees of those polynomials k1, k2, somewhere in the set of the distances, from 1 to w, and let us assume that the polynomial of degree k1 is monotone from d1 to d2, and the polynomial of degree k2 is monotone the other direction. It does not matter which is greater, d1 or d2. We just need this monotonicity in different directions. Let us assume that this determinant, moreover, is positive, because we want to divide by that. And not only we want to divide by that, but we also want that when we divide, the inequality does not flip. So it's positive. Then the size of the code is as shown here. This is in fact very easy to prove, having these assumptions, because let's see. So remember, we have two distances, and so our Delsart problem, in fact, has just two coefficients, 1 and 2. So let us say those f1 and f2 form a solution of the Delsart problem. Maybe unique, maybe not unique, it doesn't matter, just the optimal solution. Well, then the size of the code, as Delsart tells us, is 1 plus f1 plus f2 at most. Very good. So let's write the two Delsart inequalities, and if you add them up, then you obtain this, manipulating the values of the polynomials. Write this as determinants, and then we have this plus that, f1 plus f2. And well, what is missing from this bound is plus 1. So let's inject plus 1 that adds something extra, which we deduct here. And we have this inequality, and as we said, we can divide by this determinant, nothing is disturbed. So divide and get the answer. All right. Now, of course, bounds for codes with a fixed weight can be phrased as related to the Erdős-Corrado theorem, EKR theorem, which says that, so that is a particular case of my few distance set problem, except that the distances for the EKR theorem have to be consecutive. It is typically phrased as maximum cardinality of intersecting families of subsets, but if we move from families of subsets to their indicators, then of course we get an equivalent formulation using constant weight codes. So the theorem says this is a known result. This is a particular case of EKR, but I'll just show how that follows from that little theorem that we had on the previous page. So if the distances are 1 and 2, then the maximum size is n minus w plus 2. Choose w. For that, we take the degrees w minus 1 in the theorem. Well, Hahn polynomials at 1 and at 2 can be computed explicitly for any degree, including w. So we compute that. And then we check the conditions. And the question is, when are the needed quantities positive or negative, as we have assumed? And it turns out that the answer is, starting with that n, all the signs work our way, and we can prove the result. Now, this is known, and this is not particularly exciting, except for one little remark. So the Iker-Erdős-Corrado theorem was proved starting with some n, and it was not very clear if that the minimum n or not. In fact, they knew from the start that that was not the best. And there was this famous paper by Rick Wilson, about 1981-83, if I remember correctly, where he said, well, this is this lowest n from where it works. That was a highly non-trivial extension of the Iker theorem. And what is interesting is that this quantity is exactly Wilson's condition on the dimension. So, yes, it recovers it. I still don't know why, but okay. Very good. So it proves the result. How do we do this for S2, 3, and 4? Well, the theorem says that, let's say, for weight 4 with 2 distances, the maximum size is like that. Take the degrees as shown here. W plus 1 minus di, it's the same as before, so we are taking the same degrees. Now, there is a condition that says if we move to 2 distant spherical codes, then the inner products have to be algebraic integers, have to satisfy some rational fraction condition. And if you translate this back to the binary space, then the only pairs of the distances we must consider are those. So let's consider them. For instance, 1, 2. We write again the needed inequalities, and as you see, everything works our way once n is greater than 9. So that's how this 9 comes up, generalization, and we have the result. Well, yes, for n greater than 9, the fractions are non-negative, and the cardinality is, once we substitute into our formula, we get the answer. And we get the bound, and it is easy to construct codes of that type. And so we have the, right? And then, well, I will just say etc. Because we proceed in the same manner. It becomes it progressively becomes computationally more intensive because the determinants become of a larger size, 4 by 4, but it still works up to a point when it stops to work. And that's where our theorem stops. And let's see. Yes, we also derived an asymptotic bound, which is, well, of course it's asymptotic, so it is not as precise as the other results. But it says that for any pair of distances, any w, the maximum cardinality is n squared times this constant, where the constant can be computed up to little over 1 as the dimension of the space increases to infinity. And that is proved exploring some asymptotics of Hahn polynomials. That's a somewhat isolated result. Yes, and this bound is tight for two notable cases, 1 and 2 and w minus 1w, and the tightness is established, it is related to the famous Johnson bound for constant weight codes, but also existence is a celebrated result of Wilson on the existence of BIVDs, balanced incomplete block designs. So sometimes it is tight, otherwise we don't know, but anyway we have this asymptotic result. Well, final musings. We know that once Wilson's result stops, it becomes really difficult. So it was not known for a long while what is the minimum n to which the Iker theorem works and what is the answer. But elsewhere, Khachaturian gave this answer at some point, the complete intersection theorem. So we asked ourselves, well, maybe we have this little application of linear programming to Iker type results. Can we do also with Khachaturian? Well, no, we cannot. It is still tantalizing if that were possible, but maybe it's not. So what about the Iker theorem itself? finally, let's state it. It says, if the distances are, previously I mentioned 1, 2, but now let's go to W minus T. So this is the T intersecting families of subsets. Then the maximum size of the family is this. For all S, well, of course, up to W minus 1. And this is a full form of Wilson's lower bound in the dimension. And it is easy to construct such a family. So we simply take all the subsets that contain a fixed T subset. T is W minus S, and we get exactly that binomial coefficient. And the EKR theorem was that we cannot have more, starting with N, according to Wilson, greater than satisfying this inequality. So we experimented with that, trying again LP, trying some numerical experiments. We didn't do much about that, but we have this somewhat, oh yes, sorry, no, it's not quite right. So we showed that if S is W minus 1 distances, then the answer is that. How is that different from the EKR? Well, we do not insist on the distances being consecutive. We can skip this one distance anywhere in the sequence. And that is done by connecting the EKR theorem to a group of results on combinatorics about codes with missing distances. Frankel and Furedi, notably. So we have this little claim, which was a part of our main theorem, our table. But based on our experimentation, we make this somewhat, cheeky conjecture. Not only for consecutive distances, but for any S distances, the maximum size is that. Well, somewhat fascinating, but it's just a conjecture. And the EKR theorem corresponds to consecutive distances. What else? Well, I guess that's it. Thank you.
Okay, comments, questions?
Thank you very much for your presentation. It's about 1 month ago, Lazirin presented this. He was very proud. Actually, what I can say about this area, many people interested about it, but results, it's not easy to get any new result, especially Hungarian. But in this presentation, this paper, we use this, Delsat method.
Yes.
Everything, if you can compare with Hungarian mathematicians, very often. Okay, my question is, I already asked Lazirin, but I don't remember his answer. You're using for previous theory, right? For about the two distance set.
Yes.
Yeah, you use LRS.
Yes.
My question is, can we use Hiroshi extension of this theory?
Well, in fact, not only I can, but we did.
Where?
Where? You see, when we... let me answer. So we use that when we need to establish lower bounds on N. Sometimes the conditions of our theorem fail for low N. Let's say we can prove it starting with 35, but we want to bring it to 15. Not that that would make much of a difference for the mankind, but just to push it somewhere. And to do that, we first take Hiroshi's extension and your work with him. We only locate the pairs or triples of the distances that we need to consider. And for them, we check it by hand, for instance, semi-definite programming. And we rule them out. And so that's how. That's how we can lower the N in our claim. So we did use it. It's
maybe that's the answer we expected, but
probably he also answered similar.
Computation, in fact, it's rather intense.
That means it becomes more and more complicated, right?
Well, you see, if we're content with starting with N50, then we don't need to do that. But trying to push this down, it requires more of an effort.
So, do you have any open problem? Do you have some problem that it can be solved because it is maybe the scope?
No, the method is largely exhausted. You see, the thing is that we stopped at let's go back. This idea ends pretty much where this table ends. That's it. I cannot do more, and I don't think it is possible to do more. This EKR conjecture, a related conjecture of interest, we don't have an approach. But still, this is something new, right? I guess it's okay.
And it's nice, yeah. Okay, any other? Thank you again.
Thank you.
So our second talk will be delivered by Ilya Vorobyev, joint work on coding and feedback. Please.
Thank you very much. Yes, this talk is based on joint work with Christian Deppe, Vladimir Lebedev, and Alexey Lebedev. And I will start with this simple combinatorial search problem. So let's say that we have a set of integers from 1 to m, and Alice chooses one number, x, from this set, and Bob wants to get this number by asking questions, yes or no questions. So basically you can ask, is the chosen integer belongs to some set? And well, the question is, what is the minimum number of questions he needs? And we can consider sequential or adaptive search, like he asks questions one by one. So he asks a question, he receives answer, and then he thinks about the next question and so on. And this is a very simple case, and he obviously can implement something like binary search, and then the answer is well, binary logarithm of n. Okay, also we can consider non-adaptive search, and it means that he thinks of all his questions in advance, and he sends the list of his questions, then he receives a list of answers, and then he needs to give an answer. Yeah, in this case, we can represent his questions with a matrix. So here we have m equals 8, we have 3 questions, and we put 1 into intersection. If so, basically here, his first question is the number x belongs to the set 5, 6, 7, 8, yes, and so on. And then he just receives answer. So for example, if Alice chose the number 5, then he just receives this binary representation basically of 5. So it means that in this case, for non-adaptive search, we actually need the same number of questions, and so it's also very simple to solve. Okay, so now what if Alice can lie? How will problem change? Okay, let's start from non-adaptive or non-sequential search. So if we again use this matrix representation, then let's say there was a number 5 which was chosen. So those were the questions. But the answers now, we can have one error here. If Alice can lie 1 time, we can have 1 error. So basically, instead of this column, we receive the same column, but some number of symbols is changed. So if Alice can lie 1 time, then 1 symbol is changed. But to find a number in such setting, we can use a single error correcting code. So if we write our code words as columns, then even if 1 symbol is changed, we can of course find what was the original message for column and find the chosen number. So it means that this problem of non-sequential search with 1 lie is equivalent to constructing a single error correcting code. And if the number of lies is t, then we need a t error correcting code. Okay, this was about non-sequential search. But okay, so if we are talking about sequential search, then we just need error correcting codes with feedback. It's a little bit harder to see that it is also equivalent. I don't want to talk about this equivalence, just say yes. Sequential search is equivalent to error correcting calls with feedback, and number of lies is equal to the number of errors. Okay, so such kind of problems can be investigated in the language of these combinatorial search problems and in the language of codes, and we will use the language of codes. Yeah. So we can formally define what coding with complete feedback is. So we just have some set of possible messages, and sender chooses one of the messages. There are we have this input and output alphabets, and basically sender has this encoding algorithm which for each message and each prefix it gives like the next symbol. Yeah. And Y here means the received cohort. Yeah, and the number of errors can be defined as the error vector can be defined as this received message minus sent message, and the number of errors is just the number of non-zero coordinates. So this is coding with complete feedback because at each coordinate depends on all previous received symbols. We can also consider coding with K instances of feedback. It just means that code length is divided into K plus 1 parts, and we also need to send one message. And now we have these encoding functions which depends on big and I symbols, where an I is just symbol of this some first parts and I. Yeah, so we can adapt our strategy just at some specific moments. Yes, and it gives not one next symbol, but an I plus 1 next symbols. Okay. So here, at first we consider the case of one feedback and also one error. So let's consider one strategy. So let's say at first step we transmit an arbitrary sequence of length n1. Okay, let's say we don't have any errors at the first n1 symbols, and we know that we can have at most one error at n2 symbols. Then we just need to use a single error corrected code at the second stage. Okay, so here it's clear. But also we could have an error at the first part, and then we need to correct this error somehow. And okay, so we transmitted the sequence U, and the received sequence was different. It was sequence V with one error, and we already have some code C of V, which is used in case if there was no error. So to correct error in the first part, we use 3 points of this code. What I mean by 3 points, so if we look at code as a set of spheres, so we are talking about one error here. So each code word, we can imagine that we have, for each code word we have a sphere with a center at this code word and radius 1. These spheres obviously don't intersect each other, but if they don't cover all space completely, some points don't belong to any of these spheres, we call these points free points or free sequences. So these points are used to correct the error. And such strategy was used by Basiliga to prove that with one feedback we can, for the case of query symmetric channel, we can transmit asymptotically optimal number of messages. So the number of messages, if you compare it with Hamming bound, it's asymptotically the same. It can be achieved with this strategy. only with one feedback. Okay, so now we formulate the theorem. So let's say we have some alphabet Q. We have some channel. It can be arbitrary channel actually. Well, but okay, let's think about symmetric channel. And we can transmit such number of messages. Number of messages is the sum of m of u, where u is a sequence of length and 1. So for every sequence we have some number. Only if we have a family of singular recurring calls of length and 2, cardinality m of u and f of u is the number of free points, and we need to have this condition. So this condition basically means that if we have some sequence v, and we look at all sequences u which are at distance 1 from it, and we sum the number of messages, it should be at most the number of free points in the code for sequence v. Yeah, so it's basically the proof of this theorem is proved with this strategy I tried to explain on the previous slide. Okay, and so if you look at this theorem, what is the problem with it? That it is formulated in terms of some family of calls, but even if we fixed n1 and n2, how do we find this optimal family of calls? It's not completely clear. It can be formulated as a linear program, but yes, we need to have some tables of these calls with good parameters m and f. So if we are talking about symmetric channel, of course there are such results. If we are talking about some, for example, binary asymmetric channel, probably not so many results are known. Yeah. But we can, for example, we can take the same code for every prefix u, and even this simple case can give sometimes a good result. So, for example, as one of the corollary, we can have this one. So, if we have a Curie symmetric channel, then we can construct, and the length is at most q plus 1. Then there exists a code with one feedback and size q to the n minus 2, which corrects one error. So it's in a way similar to Reed-Solomon code with one error, but here we don't need q to be a prime power. Q can be arbitrary. Yeah, and to prove it with this theorem, we just take n1 to be equal n minus 2, and 2 equals 2, and as a code, C of u, we just take a code with one code word, let's say 0 code word. Then we can compute the number of free points and verify this constraint. So it helps. So the theorem can be applied, and so we have this code. Yeah, it's just for one error, and I will talk a little bit later about the generalization for the case of 2 and more errors. Yeah. Okay, and another corollary, we can take again arbitrary q. We can take length equals q to the k minus 1 divided by q minus 1. Then the number of messages which can be transmitted is equal to the q to the n minus k. So it looks like Hamming code, but again q is not a prime power here. Okay, so there is no proof. Yeah. Okay, so there is another. We have another way to construct algorithms codes with feedback. And okay, so if you have a code with feedback, so code without feedback can be represented as a set of spheres. If you talk about code with feedback, now we are talking about the set of, let's say, clouds. So it's a set of sequences which are decoded to one cloud. Is a set of sequences which decoded to one message, and they also shouldn't intersect. So if you compare this problem with, well, they have some specific form, but they are more flexible than spheres above. So we have more freedom, and sometimes we can pack more clouds than balls. That's fine. Yeah. And we present also an algorithm which allows to construct a cohort of lengths n with k feedbacks from the cohort of length n-1 with k-1 feedbacks. And we call this algorithm double and delete and data for short. Okay, so basically the idea of this algorithm is we take a cohort for length n-1 and we take each cloud, and from each cloud we construct two clouds. So to construct the first cloud, new cloud, we add 0 as a prefix to each sequence, and for the second cloud we add 1 to each sequence. Yeah, and these new sets, they are not really clouds, they don't work, because if we have an error at the first symbol, we have a problem. So if we have an error in this first symbol, we can obtain some sequence which is not in the set. And that's why we call it incomplete clouds. But to fix it, we just need to add one more sequence to each cloud. So if we added 0 as a prefix, we need to add actually arbitrary sequence which starts with 1 to fix this incomplete cloud and to make it like normal cloud from it. And we use 3 points to do it. And so we add some 3 points to these incomplete clouds and make them complete clouds. And we do it until we don't have any more incomplete clouds, or we don't have any more 3 points. Yeah, but if you don't have any more 3 points, then if you don't have any more incomplete clouds, we just terminate this algorithm. We stop here. But if we have some incomplete clouds, we take 2 incomplete clouds which start from different symbols, we destroy them. By destroying, I mean we just make all of these points 3 points, and we use these new 3 points to like transform some incomplete clouds into clouds. So this is step. This is the first step. Is double step. This is the delete step. Yeah, that's why we call it algorithm like this. Yeah, and we repeat this step until we don't have any more incomplete clouds. So this idea gives us the following theorem. So if on length n-1 we had a code of size m of n-1, then the new size of the code is expressed with this formula. So if the size of the previous code was small enough, it's just doubles. And if it's close to the Hamming bound, 2 to the n over n plus 1, then it equals u of n or u of n plus 1, where u of n is just a maximal even number which is at most Hamming bound. Okay. And for example, we can use this algorithm to prove again this result by Pelch. So in the case of complete feedback and 1 error, the optimal number of messages is known. It was computed a long time ago. But our algorithm allows us to repeat this result in 2 lines. So this is the optimal number of messages. It equals u of n or u of n plus 1, depends some inequalities. And basically to prove this theorem with our algorithm, we just need to prove that, let's say by induction, we prove by induction, prove that this number of messages on length n-1 is big enough. And then we can use this data algorithm and we obtain this. So it's really proved in like 2 lines, and for some small numbers we can check that everything works. We can check it manually. Okay, so we can prove this old result again, but also we can prove something new. So the previous result was about complete feedback, And now we can prove that only with 2 feedback and 1 error we can actually achieve the same result. So instead of complete feedback after each symbol, we now have only 2 feedbacks, but we can transmit the same number of messages. And to prove it, we actually use the theorem, which I was talking about in the beginning, to construct a good enough code with 1 feedback, and then we can make it better by using this data algorithm one time. And then we obtain a code with 2 feedbacks, yes, which transmits the same number of messages as a code with complete feedback. Okay. Then we can do the same thing basically for the query case. So we can generalize our data algorithm into a query case, and this theorem describes the parameters of code which can be obtained with this algorithm. But basically the idea is that we have this Hamming bound, and if the size of the code of length n-1 is small, then we just multiply the size by q. But if it is close enough to Hamming bound, it equals to this thing u of n, or u of n plus something small, where u of n is the biggest number which is divisible by q, and simultaneously smaller than or equal to the Hamming bound. So it's very similar, and again we can obtain the result about the optimal number of messages for complete feedback. So it was for query channel, it was proved computed by Egner, and again with our data algorithm we can obtain the similar result, the same result, just in this similar idea. Again we construct a code which is good enough. We just prove it with induction, and once again we can strengthen this result for the case of 2 feedbacks, but here we need q to be a prime power. It's not proved for all q of n, but for the case when q is prime power, we can transmit the same number of messages as the algorithm with complete feedback. We can transmit it with only 2 feedbacks. Yes. Yeah, and this is proved again with the theorem from the beginning. We construct a code which is close to the best code, which is close enough to the Hamming bound, and then we use this data again one time to make it optimal. Okay, so yes, it's proved only for q which is prime power. When q is not a prime power, we can, for every q, we can prove it for n which is bigger than something. For example, for n which is bigger than q squared, but yeah, I think it can be proved for any q, and then we are working on it. Yeah, so now I will talk a little bit on the case when we have more than 1 errors. For example, if you have like 2 errors. So previously we need some code and some number of free points. Free point can be considered, you can think of free point as a sphere of radius 0 actually. But now we will need a set of spheres of different radiuses, let's say from 0 to k, and all these spheres shouldn't intersect each other, and we will call such family universal family, such vector of sizes. And for example, we can generalize the theorem from the beginning into the case of 2 errors. You can generalize it for the case of k errors as well, but I just wrote it down for 2 errors. So again, we can transmit this number of messages. This is the sum of this m2 of u, and 2 of u is the number of spheres of radius 2, and we need to have this some conditions. Yes, and then we can have such code. But you see that when the number of errors is bigger, then it becomes more complicated. So at the beginning, I showed that we can have something similar to Reed-Solomon code for one error, even for the case when Q is not a prime power. The question is, can we have it for any number of errors? Can we have a code with size Q to the n minus 2t for Q with one feedback, for the case when Q is not a prime power? And for the case of two errors, we can say that yes, we can apply the theorem. So I don't think I have a lot of time, so I just briefly say you can apply the theorem, and we need a universal family with the parameters. For example, with one sphere of radius 2 and Q minus 1 squared spheres of radius 1. And then if you take like n equals Q plus 3, then condition will be satisfied, but the question is how to construct such family. And such family exists because there are Latin squares. So Latin square, I think you know that it's the m by m array filled by m symbols such that each occurs exactly once in each row and each column. And Greco-Latin square is a pair of orthogonal Latin squares. So for example, here we have Greco-Latin squares of order 3, 4, and 5. So big letters from one Latin square, small Greek letters from another one. And if we write it simultaneously in one square, every pair appears exactly once. So this is called orthogonal Latin squares. And they give us the codes of length 4 and distance 3, which is exactly what we need here. So from these Greek Latin squares, we can obtain a family, universal family that we need. And we constructed a code with one feedback and size Q to the n minus 4, which corrects two errors. We're still working in the case of even more errors. For the case of even more errors, we can only have such theorem for now. We can have a code with 2t feedbacks of size Q to the n minus 2t correcting to t errors. And the proof of this theorem is based on the theorem analogous on the first theorem with universal families and so-called rubber method, which was proposed by Lebedev and Tepe, I think. Yeah, but I think that's all I wanted to tell today.
No questions, comments? I think everybody is moaning for the coffee, so it's coffee break. Thank you.
Progress.
So welcome to this last presentation of this afternoon session. Ivan Ladja will talk to us about W-admissible partitions and some identities related.
Thank you. I'm afraid the subject of this talk is a little bit off target. The conference was spherical stuff. I was thinking of something, this was the closest I could think of. Of course, it has some relation to linear programming. The Makhilov type identities, the Kravchuk polynomial show up in some very special versions of the Makhilov identities, but this will be about coding theory. But there was a certain bias towards coding theory in today's afternoon session, starting with Sasha Barak in the next talk. So, Makhilov type identities. And as I thought of this, we have the 60th anniversary because the year which we usually connect identities with is 1963, so we have 60 years. And of course, the classical form, or what J. Wood calls the model theorem, is probably this. We have a code of our finite field equivalence of length n. The orthogonal code is defined in the usual way, and if the capital I's within this is denote the number of code words of Hamming weight I, we connect with the code, the so-called weighted numerator, which is this polynomial in two variables. I prefer to write this in two variables. It's possible to write it in one variable. And if this is the weighted numerator of the orthogonal code is given by this expression. This is the most familiar form, but there are many other forms in which we can write the Mach-Williams identities. For instance, this, which is rather combinatorial because it suggests that we can prove the Mach-Williams, the classical Mach-Williams identities by counting in two ways. In matrix form, if this is a vector, the so-called spectrum, here the 1 is missing, A1. Then the matrix A is some number times a matrix Kn, which is this matrix, which is denoted by K because the Kravchuk coefficients show up there, and this is the spectrum of the orthogonal code. This was taken from Simone's paper from the 90s. And so these are the classical Mach-Williams identities. There have been many proofs during the years, starting, most of them rely on characters, but there are some combinatorial proofs. Very nice proof using partial derivatives by Van Wart, again somewhere in the 90s, but I don't know whether you're familiar with this. This comes from Thomas Holland, Technical University Munich, now Hangzhou University, China. Zhejiang University, Hangzhou, China. If this is the weighted numerator, this is the weighted numerator of the orthogonal code. Well, consider this automorphism of the ring of polynomials in two variables with rational coefficients. Consider this automorphism, which to the polynomial f, with this polynomial associates the polynomial f. Well, the first variable is replaced by x plus q minus 1y, second variable x minus y. If we consider this automorphism, the Mach-Williams identities are equivalent to the following statement. The image of the weighted numerator of the code C is C times the weighted numerator of the orthogonal code. This is the same thing. So, certain automorphism of this ring sends weighted numerators to weighted numerators of the orthogonal code. This is one form of the Mach-Williams identity. And the proof's nice. How can we prove this? By induction. Induction on the length. For codes of length 1, we have just two codes. The zero code just a 0, or FQ itself. And for them, it's very easy to check this, just an easy check. This is straightforward. Then the induction step, this is nice. First, if S and T are two, not codes, just sets of vectors of length n, the weighted numerator of the union of S and T is the weighted numerator of S plus the weighted numerator of T. This is straightforward. Then we consider this mapping, which is sometimes called puncturing of the code. Each word is has as an image under pi. Well, the same word, just the last component is deleted. And if C is a code, by C0 I denote the subcode with last component 0. I still do not delete this last component. It is there, just this is a subcode, then this is well known. Well, then I have the following two identities. A, C, the weighted numerator of C, is x minus y, the weighted numerator of the code C0 punctured, plus the weighted numerator of the code C punctured. Well, this is actually the shortened code. They sometimes call it the shortened code. If I take all the words with last coordinate 0, remove it, this is the shortened code of dimension 1 less, by the way. And for the orthogonal code, I have x minus y, the weight numerator of C, the punctured C perp, and the weight numerator of the punctured C0, this is the shortened code, perp. Well, these two, they're not that difficult, but, if they're not entirely clear, well, let's write down all the, this is the code C. And the code C, this is a linear code, of course, and I write it as C0, C1, C, let's say Q minus 1, and the first part consists of all the words that have last component 0, last component 1, last component alpha Q minus 1.
How it will work if the last component? How it will work if the last component is constantly 0? It could be so.
Yeah, but well, it will work. It will work. I skipped one part. This is in the trivial part. Yeah.
But still, it's got to be considered.
Yeah. You're right. But this is the essential part of the proof.
Yeah, it's non-trivial part.
The non-trivial part. The spectrum of AC0 is then the same as the spectrum of this one, just this one shorter. So these two are related like that. And for all the remaining stuff here, Cj, for all the remaining here, I have A Cj equal to y, because the weight of each code word is reduced by 1 for all the remaining if I remove this part. Okay, and then summing all these, I get the spectrum of the code C. On the other hand, this is x a by C0 plus the sum of a by Cj, which is x minus y, here the y, x minus y a by C0 plus y, and the sum of all of this is a by C, and we are done. Actually with the first thing. The second thing, well, let's say in some similar way. And then this is the nice part. What do I have to prove? I have to prove that the image of AC is C times the image of C perp. Well, apply alpha to both sides of this. You get this. Alpha of x minus y, x should be replaced by x plus q minus 1y, and this gives q times y. Write it down. And by the induction hypothesis, because these codes are shorter, these two, and we assume that the theorem is proof of shorter codes, this is the cardinality of C0 times the spectrum of the shortened, the punctured C0 perp, plus x minus y, here the y, the image of y is x minus y, times this. And now we have to see that q times the cardinality of 0 is exactly the cardinality of C, because the dimension of C0 is by 1 less, and if here in the parentheses I have exactly this expression, and that's it. So This is the idea of the generalization. Actually, there are several directions in which the Mac-Williams identities can be generalized. First, we can change the ambient space, not FQ to the power n, and something else. Then the notion of orthogonality. Third, the spectrum. And the spectrum is usually connected to some partition of the ambient space. Oh well. And our tool will be such we want to define certain automorphism of certain ring of polynomials which sends the weighted numerator to the weighted numerator of orthogonal. Of course, many such things have been made during the years, and one should mention already in the book by Mac-Williams and so on, there are many different weighted numerators, but this is the nice thing. Delsart considers additive groups, and the code is just a subgroup in the additive group, and the orthogonality notion is just the star, the character. But the group of characters is isomorphic to the group, so the ambient space remains in certain sense the same. Later on, this is quite important, Clem wrote Mac-Williams identities for codes over integer residual rings. Well, this is just another proof of Mac-Williams identities, but this is rather nice because he wrote Mac-Williams identities, Urian Simonis, for different coordinate partitions. This is quite important paper. This is in the lines of Delsart's work. A abelian group of codes is a subgroup of the abelian group. The character group, well, the orthogonal code should sit in the character group, but the character group is isomorphic to the group A, so we can consider the orthogonal code to consist of group elements, and psi is just an isomorphism between the two groups. And Thomas Eriksson and Ziznoviev, they consider the so-called Fourier transform, which is in this form, and so-called F partitions or Fourier invariant partitions. This space of all the maps from the group A to the complex numbers, which are linear combination of the characteristic functions of the parts of the partition. Here P is a partition. Say the P sub i's are parts of the partitions, and chi sub I is the characteristic function of this part. Well, this should be invariant under the Fourier transform, so it should be mapped to itself. Well, if we have such an n partition, there is a nice theorem. The spectrum with respect to this partition, and the spectrum is defined in the usual way. The number of group elements from the code, because the code is a subgroup, which are contained in the particular part. This is the A sub I, and all the A sub i's, they form some vector. And the vector for the orthogonal code is some matrix times the vector of the original code C. Here, this matrix K consists of some coefficient K sub ij, which are of this form. Here, the term 1 over C, the cardinality of C, is in the coefficients, put in the coefficients. They had in mind their things. In this paper, they think Rishi Boletansky for advising them, we don't remember. Well, this is another a nice paper. They can prove using this all the known up to this moment, the Mac-Williams identity, all the known up to this moment. Mac-Williams identities for the various partitions. Well, what is hidden here? Actually, the orthogonal code is in the group but it's actually not in the group, it's in the character group. In this case, the character group in the group itself, they're the same, so there is no big problem, but sometimes, as in the Frobenius ring, they might be different, and we might have, we should say something in this case. Well, Sasha-Nechayev and J. Wood, they pioneered the investigation of so-called Frobenius rings. Frobenius rings, they thought that these are the rings which are important for coding theory, and this is a rather large class of rings. They contain all the chain rings, but also various matrix rings and all that. Okay, so what are Frobenius rings? Frobenius rings are finite associative rings with identity. These are three equivalent definitions. We shall use the first definition. There exists a function from the ring to the rational numbers, which is 1 at the 0. At associative elements takes on the same values, and is 0 on all ideals, left or right. Nakayama's original definitions is different. Do we have nice examples of Frobenius rings? Yes, of course, all integer residual rings are Frobenius rings. All finite chain rings, in particular the finite fields. Finite fields is trivial chain rings with no ideals, at which Bernard Heiser made the remark, I wouldn't call a finite field trivial. Direct products of Frobenius rings, matrix rings over Frobenius rings, group algebras over Frobenius rings are against Frobenius rings. And the code, well, our ambient space will be R to the power and all the n tuples over the ring. Codes will be subsets, but if C is an R submodule, left or right, because of course I didn't mention that, but Frobenius rings are not necessarily commutative. So we should distinguish between left and right. If we have a submodule left or right, the code is said to be linear. It should be either left or right. Orthogonality is defined in the usual way. This is the nice and probably the crucial property, that the right orthogonal, if C is a left linear code, then it has the right orthogonal, and the right orthogonal has left orthogonal. If I take first the right orthogonal, then the left orthogonal, I get again the C. And similarly for right linear codes. And the lattices of the submodules of these modules, the left and the right, they are anti-isomorphic. This is well known. Now, we consider the Q space of all functions from the n tuples of ring elements to the rational numbers. All functions. We can define different products there, like juxtaposition, convolution, and so on. But the function is said to be left invariant if it is invariant other left multiplication, and similarly for right. And the space of all left invariant functions is Qs, and Qt is the space of all, well, this should be right, of course, obviously, copy paste. And this is easily proved. The characteristic function of the late linear code is left invariant, and the right linear code is right invariant.
Sorry, just to follow. Yeah. R star asterisk, is it?
R star are the units. Are the units of the ring.
That's only inversible elements.
Yeah.
Okay.
The units of the ring. Sorry. So, and we go along the same lines. We define the Mach-Williams transform. The Mach-Williams transform, which is a map of all the mappings of QR diamond. Well, the diamond is just the sum of all the QR. It is defined by this formula. We have a function f, and the image of the function f is given by this function The omega is the thing we had here in the definition of this omega, which was necessarily unique in the definition of Frobenius rings. And similarly, the right counterpart, which we denote by W0. So, for every left linear code, the image of the characteristic function is the characteristic function of orthogonal complex can be brought down. And this is actually a Mach-Williams identity if we consider the trivial partition of the ambient space. Each element of R to the power n is a single element in its path. So if we consider this trivial partition, for this partition, this is just the Mach-Williams identity. And similarly for right linear codes. And of course, this Mach-Williams transform behaves well with respect to the different multiplications. If we take WFF and W0, WFF, this is of course F itself up to a certain factor. Also these properties. So much for Frobenius rings. Now we consider partitions of the ambient space. The set of all partitions, of course, can be made to a lattice with respect to the usual partial order defined by inclusion. Defined by, I would say, refinement here. I don't know. I've written inclusion here. The smallest element, this is the partition of the ambient space in which every single element is a single element in a group. And the largest element in this lattice is where we have just one group of all the elements. This is the complete around. And all the partitions are ordered somehow. And a partition is bigger than some other partition. If the smaller one is a refinement of the big one. Okay, we can, given partitions of this space in different parts, we can define, for instance, the Cartesian product in the usual way and the Cartesian power in the usual way. So we have partitions, but not every partition, and the strategy is clear. We have the ambient space, we consider a partition of this ambient space, and the spectrum of the code will be the number of code words contained in a particular part of the partition. We can write this as a vector. But not every partition admits Mach-Williams identities. So if L is a partition which has parts L sub I, and R is another partition of the ambient space with parts R sub j, the ordered pair LR is called a regular pair of partitions. Regular pair of partitions if for every two indices I and j and every element alpha from the ring there exists constants lambda sub ij upper index alpha and rho sub ij upper index alpha. Well, they are similar. This is with respect to the right formulation of the thing. So consider lambda sub ij with upper index alpha, such that for each x from Li, there exists exactly lambda sub ij alpha members in Rj with dot product alpha. And similarly here, for every y in Rj, there exist exactly this many members. Well, these numbers do not depend on particular member of Li or Rj we take. They're the same for all members. So such a pair of partitions is called regular. A single partition is called regular if PP is a regular pair. Right? Do we have regular partitions? Yes, plenty. If P is a partition, by this we denote the linear span of the characteristic functions of the members of the partition. So each subset in the partition has a characteristic function, and we denote by this the space spanned by these members. Here the maximal element of these two partitions, which is up, can be constructed in this way, and the minimal element of these two partitions is constructed in this way. So we can construct many partitions. But we are interested in W admissible. W stands for McWilliams, maybe. Not maybe, McWilliams. Partitions that admit McWilliams. It will turn out that they will admit McWilliams identities. A pair of partitions is said to be W admissible if this space spanned by the left partition, its W image is in the space, contains the space spanned by the right partitions, and similarly for the right counterpart. And a single partition is doubly admissible if the pair is doubly admissible. So it turns out that LR is doubly admissible if these sums, they do not depend on the particular choice of X in Li and Y in Rj. And the matrix formed by these coefficients is traditionally denoted by K, and this will be the K matrix from the Ericsson Sofia paper, in the particular case for the abelian groups. By the way, I didn't mention that every abelian group can be turned, well, the abelian group has just addition, but we can produce from the abelian group a commutative Frobenius ring by a particular definition of the multiplication. I don't want to go into this, but these are the, if it is given in terms of some idempotence, then the multiplication is defined in a single way, in a particular way. So a sub I squared is E sub I, and E sub I, E sub j is defined by 0. It becomes a Frobenius ring. So we have regular partitions, and on the other hand, we have doubly admissible partitions. And it turns out that every regular partition is doubly admissible. Every regular partition, and the partitions from the F partitions from the Fourier transform, they were regular. Every regular pair of partitions is doubly admissible. But the converse is not true. For instance, this partition, consider just R to the power n, and here in one group the 0 vector and all the remaining vectors in another group. This is always doubly admissible, but is regular if and only if R is a field. If there are non-trivial ideals, one can easily check that this is not. And there are also other examples. Okay. So, if these two partitions are doubly admissible, this is also doubly admissible. And if these two are regular, then this is also regular and doubly admissible. So we can plenty of doubly admissible partitions, though we don't know whether, no, we certainly know that not every doubly admissible is regular. But how can we construct doubly admissible partitions? We can construct from orbits of groups. We can consider this group, gamma L and R, which is defined in the very same way as the gamma N Q. And it acts on both sides of the ring by a certain. Here, the first element, the elements of this group can be considered as pairs, pair of a matrix and automorphism of the ring. And they act in a certain way of the interpose of the ring. So, if G is a subgroup of this gamma L, LG is the set of orbits of the groups on Rn, and RG is the set of orbits of Rn with respect to the right action, because we can act with the elements on the left and on the right. So, if these partitions are G invariant, so the parts of our L and R are fixed, then this partition, the maximal element of L and LG and the maximal element of R and RG, is called the fusion of these two. And now we have that for any subgroup, this is a doubly admissible partition, and in particular, if this group is not just subgroup of this, but also of GL, the general linear group, the automorphism is identity, okay? Then this is even regular. And a similar result, if G is a subgroup of gamma L, and if LR is G invariant doubly admissible pair of partitions, then so is this. So we have plenty of partitions. What does this mean? For instance, we can consider finite field, the n tuples over finite field, and GLN, for instance, not gamma, GLN, GN cube acts on the FQ to the end, and the orbits under the action of G can be considered the parts, and the spectrum is just the intersection of the code with these different orbits, and this will admit Mach-Williams identity. Well, I should be fast, but I'm close to the end. So we consider a partition of the ring. The spectrum of the code is defined in the usual way. The intersection of the code with the parts of the partition, and this can be considered as a vector, and this is called the weight spectrum with respect to the partition. And let LR be a doubly admissible pair of partitions. These are the part of L, these are the part of R. The spectrum of the code with respect to the left partition is this. With respect to the right partition, I denote it by BC, but this is AC perp actually. So we have now this theorem, and these are the Mach-Williams identities for Frobenius ring. If LR is doubly admissible pair of partitions, then these are the intersection matrices. And if C is a left linear code, the spectrum of the left linear code of the orthogonal code, the one was AC, the other was BC, are related by these identities. This is a vector, this is a vector, this is a matrix. And similarly here. Well, here the Mach-Williams identities are in the matrix form. One can write, I haven't done this explicitly, but one can write this also in polynomial form. In the polynomial form for chain rings, this is how the Mach-Williams identities look like. Chain rings, just they are rings in which all the ideals form a chain, like Z4, Z8, but also many others. Galois rings and all that. Chain rings have unique maximal ideal. The factor is the finite field. This is called the residue field. And all left or right ideals, they are powers of the maximal ideal. And the annihilator of n to the power I is n to the power m minus I. And if the spectrum this polynomial A of C is some coefficient x0 to the power something, x1 to the power something. The power denotes the elements which are the powers of x0, x1, and so on, denote the elements of the corresponding word, which are in the invertible elements in the first power of the radical, the second power of the radical, and so on. With this in mind, this is these are the Mach-Williams identities. Here is a shortcut, A sub I are these formulas, so they're not very nice. But also, if we plug in Zm, we get the matrix given by Clem. And for chain rings of prime characteristic, Doherty and Skriganov, identities. But these, we can write down identities also for certain Frobenius matrix, Frobenius rings, and so on. Well, this is about all. Actually, my idea was to define a certain partition by which one could prove existence or no existence of certain configurations, but this fails so far. Well, just the weights of a code, this is just too robust. Partition, if you have a finite partition, you might probably get better results, but so far, this kind. So thank you for attention. I'm late, of course, as always.
you want to pose any questions, please.
It's close to the end, so I don't want to alienate the audience, but I'll ask a quick question. Is it possible to phrase these results in terms of association scheme? Because Erickson's noted the result was not really about the Maclaurin's identity. It was the fact that if there is this Fourier invariant partition, then this is equivalent to having an association scheme.
Yeah, it is possible that we haven't done so. But I think there's some...
Maybe that's the next step, right?
Probably, yeah. I should move the call.
I don't know if those schemes will be commutative. That's different.
Yeah.
Maybe not.
Maybe not, yeah. But various people, Nechayev, J. Wood, they noticed that it's impossible to get a larger class of rigs. If we move away from the quasi-Frobenius rig, we don't get Maclaurin's identity.
Maybe it's not needed.
Well, because they see how far they can push the idea.
Well, you just said that even these identities could not be used to roll out some configurations.
The idea was the following. I discussed it with you, as you know. We have, of course, the wedge numerator, the 723616.
Yes.
Yeah, the wedge numerator should go to itself because itself builds.
You probably should say what that means. For the group. Because I know what it means, but maybe.
Well, in finite fields, it might turn out that the orthogonal code coincides with the code itself. But the dimension formula still goes. The dimension of the code, the dimension of the orthogonal is n. Okay, there are famous parameters 723616 binary codes whose existence is still in doubt, I think. And of course, since the orthogonal of the code is the code itself, the spectrums of the code and the Maclaurin transformation, they should coincide. But just the spectrum is not enough to rule out the existence of a code, and we were hoping that defining a certain partition, which is finite partition, probably.
That has been tried.
And
that has been tried.
It doesn't work. Yeah, this is what I wanted to say. It doesn't work. But of course, if you have the finest partition, each word in a separate class, this would give the characteristic of the function of the code itself.
Yeah, but then it's not computable.
Yeah, sure. So we would like to think of something in between, which is computable, but still leads to a contradiction. Okay.
Okay, if no more questions, then thank you.